Welcome to this video lesson. Today we will be looking at vector representation, negative and equal vectors. As prior knowledge, I highly recommend that you watch the intro video, which mostly covers component forms of a vector. Okay, for our representation, we're going to have a character which is going to move from one position to another. We're going to make a coordinate system. We're going to label the upward direction north and the left direction west. And from the figure, we can see that it's 60 degrees from west and 30 degrees from north. So if we want to write this as a vector, we write it as 40 meters, which is the magnitude of how much the character actually traveled. Meters is the unit, and in square brackets, we're going to start with west because west is the direction that it starts with, and it turns 60 degrees towards north. Or another way of writing this is starting north and turning 30 degrees towards the direction of west. If we want to write this as a negative vector, we write it as negative 40 meters, and since the directions are in the opposite direction, now west turns into east, north turns into south, or in the second example, north turns into south and west turns into east. If we want, we can also represent this using a component form. So we're going to use big square brackets, and we're going to write the x component first and then the y component second. Here we're taking east to be positive and north to be positive. And this is not the only way we can write vectors. There's many different representation. We can also write this as 40 meters with bearing of 330 degrees, meaning that if we were to draw the north direction, we would have to turn 330 degrees clockwise to figure out which direction the character is actually moving in. Now there are many different ways of writing vectors or representing vectors, but now we're going to focus a little bit about graphical representation and what each thing actually means. For the math form, we're going to start by creating a coordinate system. We're going to have the x coordinate system representing the east and west direction, and the y coordinate system to represent the north and south. We're going to have the starting position of the character at the origin, and then the character is going to move 40 meters towards its final position, and we're going to label that A. Note that our character had moved from north direction 30 degrees towards the direction of west, and if we write this with reference to the x-axis, it would be 90 degrees plus 30, which is equivalent to 120 degrees. The starting position where the character has started to move is going to be tail of our vector, and the head of the vector is going to be where it ends up at position A here, and the 40 here will be the magnitude or size, the length of the arrow, and the meter here will be the unit of the vector. We can also break this down into the two components, east and north, as we did in our last lesson. So the character has moved about 20 root 3 meters towards the direction of north because it is positive, and the character has moved negative 20 meters towards the direction of east, or 20 meters in the direction of west. To write this properly in terms of terminology, we say that the vector originates at O, that's the starting position, and terminates at A, which is our end position of the vector, or the character in this case, and their final position. This vector has started from the origin, so we can call this a position vector. Because it ends at A, we're going to call it position vector A. We can write it as a bold A. We can write it as A with an arrow on top, or OA with an arrow on top, indicating that it starts from O, or originates at O, and terminates at A. We can also write this with A with a squiggly mark on top, but this is not a very common convention. If we want to write the magnitude of a vector, in our example, the person has moved 40 meters, so that's the magnitude or the size of how much they have moved. We write the vector and we write it within two vertical lines, which indicates the modulus function, or in this case the magnitude or the size of the vector. Now let's look at negative vectors. So in the example that we have here, we have vector AB, and a negative vector to that would be a vector BA. So it kind of originates at B and then goes towards the direction of A. So it's in the exact opposite direction. And W and negative W vectors are also shown. So A, B, and BA, or W and negative W are negative vectors, and these vectors have the same length, so they must have the same size, but they have the opposite direction. Now, if we take vector BA and we take its negative, then the direction changes, it becomes AB, so AB is equal to negative BA in terms of vectors, and note that the magnitude of vectors and their negative is always the same. Now, when we're talking about equal vectors, their position does not actually matter. So if you have all these black vectors here, they all have the same magnitude and the same direction. So as soon as they have the same magnitude and the same direction, we will say that the vectors are equal. Now, the summary of this video is represented here and it's fast forwarded, so if you need to review any of the concepts, you can look at the summary section. And now we're going to move into doing an example. Now, in this example, we got a regular octagon, and we want to figure out a few things about it. We want to find or determine the equal vector to vector ED. We want to know if the magnitude of EF is equal to the magnitude of BC, and we want to determine all vectors that are negative to vector BC. If you want, you can pause the video now and try the answers before looking at the solution. Okay, to answer this question, we are going to first look at vector ED. We're going to label it, and to see an equal vector to it, it needs to have the same direction and the same magnitude, and the only vector that has that is vector HA. For the second question, we need to look at the detail of the question. It says that the shape is a regular octagon, and in a regular octagon, all the sides are the same, and therefore the magnitude of all of the vectors that are connected as the sides of the octagon will be the same. Now, for the very last questions, first we will label BC, label its opposite, which is CB, so that's one of our solutions, and the only other vector that's similar to that is vector FG, which is our second answer. Here's your practice question for the day. I will try my best to post up the solution at some point, and I hope that this video was helpful for you to get an understanding of what equal and negative vectors are.